In this video, I want to analyze the results from the previous one, right? So in the previous video, we looked at an admittedly poor measure of the independent variable in this relationship of foreign investment and the trade deficit. Remember, the theory here is that U.S. trade deficits are driven by foreign investment. We got a measure from the Federal Reserve Economic Database, FRED, and so we know that this is not a really good measure because it's FDI. It's not all the investment. It's a particular type of investment. And it's not really clear. Like I would need to go in and say, hey, okay, exactly what is included in this measure of foreign direct investment. I'm pretty sure that in purchases of U.S. T-bills are not included in that, right? So that's a huge thing, but what else isn't included? The point, and it's not net, right? It's just one side because we do invest out. So we know it's not right, but we did find a relationship. So now I want to go into putting a pin in the substantive issues or what we would call validity problems with this measure. Let's look at what the regression says, how it works, try to get an idea of, here's an example of regression in action. Maybe it'll help you to understand what regression is. So basically, what we've got here is the data, right? Underneath all of this, this is the data that we came up with last time from running regression. And I have obviously here we have a chart, right? A picture, a graph of FDI US line fit plot. Now, this is one of the pictures that you can get, one of the graphs that you can get generated when you do a regression. I didn't do it the first time, probably should have, but I reran it and now we have it. And basically what this does, this shows you we have diamonds, right? So all the blue diamonds, this is essentially a scatter plot of our data, right? We have on the x-axis, we have the x variable, the foreign direct investment in the U.S., right? And we have on the y-axis, the trade deficit. And so each point here, right, if I look at a point, right, if I roll over it, I find, hey, this is one of our observations, and this is where the trade deficit, the foreign direct investment in the U.S. in that quarter is $357.9 billion, and the trade deficit's 1111, right? That would be 1.1 trillion. So that's a lot. The thing is, though, as we look at this, each one of these, this is a scatter plot. These are all of our data. What regression does is it tries to fit a line. Now, maybe you've done things in there. You've seen Excel fit a trend line to data. That's what this is, right? We're trying to fit a line here. And these red squares, right? If we isolate a red square, each of these squares is a prediction for that value of X, right? Because basically, regression finds a line that best fits the data, right? And a line is essentially, it's an equation that associates every value of X with a value of Y. And if you remember your algebra, you might have said Y equals mx plus b, right? Y equals a slope times X and a y-intercept, right? You might remember that. Well, we pretty much have the same thing, and here's the equation that we get for a regression. We change it a little bit, y, and it's a capital Y, so it's a vector of different things. It's y sub I, right? So there's I number, for each I from 1 to n, we have the sub I means there's a bunch of different individual ones, right? But y equals beta 0, which is your y-intercept, right, or constant term, plus a slope, beta 1 times x. And there's a residual term, right? We'll get to that in a second. But basically, we have a line. And when you get regression results, you get a crap ton of results. But here we go, right? This right here is beta naught. Right? This guy up here. This is beta 1. Over here, in terms of the picture, this is what is the y-intercept of the line that the computer has come up with. And it's at 141. So when FDI US is 0, the prediction is that the trade deficit will be here at 141. And then the slope, for every increase of 1 in FDI US, we expect the trade deficit to go up 1.2. Right? Let's not 226. And that's the slope, right? So 1.226 whatever is the slope of this line. Right? Now, when you look at this line, you can see it doesn't perfectly fit, right? There's a cloud. There's a lot of variation in here that isn't explained. This is what's called goodness of fit. We actually have a statistic for goodness of fit. It's called R squared. And basically it compares what are the distances, right? For each, like, okay, here we have this guy, right? This prediction is off, right? Our prediction there on the line for this guy down here is off by the distance from this observation to the line in terms of y, which is the dependent variable, right? So that gap there is the error. This statistic, without going into how it does it, it compares all of those, right, errors that we get from this line. It compares it to what would occur if we used the mean value of the trade deficit, which would give us a horizontal line as a prediction, right? If we had no data about the independent variable, if we had no data of any independent variables, our best prediction for y would be the mean. That's the naive prediction. And so the thing is, by using this line, how much have we reduced the variation by having, instead of using a flat horizontal line to predict, by having it slope a little bit, how much have we reduced the variation in y, in the dependent variable? How much of the variation have we explained? Well, right there, 40, it's basically 0.417, 41.7, or we could call it 42%. Not nothing, but not really a good fit. And can you just eyeball this graph over here and say, yeah, I can see that it does there isn't kind of an upward slope to this cloud. So yeah, but it doesn't really fit well. That's what this is, right? Now, by the way, the one below it, that's the same measure, but it takes into account how many independent variables you have. And so it is a slightly different measure, and you use adjusted R squared if you wanted to compare a model with one or two, with a different number of independent variables. So put a pin in adjusted R squared, but keep in mind if you're doing multivariate regression, you may use adjusted R squared. All right, so I've explained coefficients, right? This is the intercept. This is the coefficient for our independent variable. This is our goodness of fit. What else do we need here? Well, p-values, right? Our p-values are the odds that the relationships seen here are the result of randomness. This is the null hypothesis, right? And we talk about there being a null hypothesis, right? So what we've got here this is scientific notation, e to the negative 10, e to the negative, they're low numbers, okay? That's 0.000, I don't even know, right? I don't even know. They're really, really low. So the odds here are not zero, but they're very, very small, that nothing is going on, right? So in this case, now you might ask, why is there a p-value for the intercept? I'm a little shady on that one too, but it's there, we do report it. But by the way, in this case, is the intercept interesting? The intercept is the prediction of the trade deficit when there's zero U.S., FDI in the U.S. Is that interesting? It might be. Also, we could, in kind of interpreting the data, say, look, if we thought that we had measured all the foreign direct investment in the U.S., which we know we haven't, but if we did think we'd got it all, right, the theory said, hey, this should be close to zero at that point. We should have, this if you use a balance of payments argument, you could make this theoretical argument, this thing should be close to zero. It is not. It is clearly not close to zero. And so we could, in this case, maybe use that and interpret it. Very often, there is no substantive interpretation. Very often, zero on your independent variable. Like if you're looking at survey results, zero income, no one has zero income. Zero age, you don't interview infants, right? And so, so sometimes zero is meaningless on these things, and for your independent variable, and therefore, but we do have that interpretation. But in looking at our p-values, right, we have to say, hey, look, there might be something going on here. We can't dismiss the correlation here as seeing Mickey Mouse in a cloud. Right? You can look up in a cloud and see Mickey Mouse. It doesn't mean somebody painted Mickey Mouse. It means you're recognizing a pattern in randomness. Well, the odds that this pattern is a result of randomness for either the intercept or the x, our independent variable, which is really the more common thing that we look at, is really, really small. So we cannot reject the null hypothesis. So that's the other thing you're looking for. Right. One thing that does come up is the standard error. When you report results, you will, in a table, you will report the coefficient, right? So you'll basically have this line, right? You'll say, okay, for this variable FDIUS, the coefficient, you list the coefficient, and you'll list the standard error under it in parentheses, right? You generally have to report your standard errors. Why? Well, the standard error goes to how far off your prediction is on that dimension. And so how well does that variable, or how precise is it at making a prediction? And the thing is that we don't really substantively interpret it, because honestly what happens is the computer calculates a standard error. It then calculates a t statistic off of the standard error, and then it consults a table, or it does something. It probably doesn't have a table in the computer, but it comes up with a p-value. So these three things are very related. The ratio of your coefficient to your standard error translates into your p-value. Bottom line, that's how it works. And so when you look at one, you kind of say, what's the ratio? The coefficient is much bigger than the standard error, so we just know that the p-value is going to be low. Other than that, substantive interpretations of the standard error are rare. Let's not even worry about it anymore. Let's just move on. And in fact, let's move on to the end of this. It's 13 minutes. I know it's kind of long, but that is everything that goes into, or that's not everything. There's a lot more things we could do. But those are the main things we look for. And hopefully you can just see this. Hopefully this picture gives you an idea. Hey, the computer's trying to find a line to fit this mess, right? And the line is defined by these guys here. Now, we do get residuals, which are, if we scroll down, here are all your residuals. These are the error terms, right? Those are those guys right there, the little E thing. But this is calculated through the regression, right? When they calculate beta naught, they calculate beta 1, and then they, based off of these, minimizing these errors. And those are the statistics. Hopefully this picture, though, is what you want to have in your mind, that we're trying to fit a line to the data. And if you can just remember the algebraic formula for a line, then all this coefficient stuff will hopefully have greater meaning to you. Will have a better, I don't know if it's intuition, but hopefully you'll understand what's going on a little better now.